All right. Okay. Well, happy Monday and happy. It's May. It's the month of May. So here we are. Um, all your semester friends are finishing school. We got 6 more weeks to go. Um, but that's okay. Um, we love the quarter system. Okay. Um, all right. Well, we'll take a look at today's lecture, and I will also post homework 3 probably later today. So just be on the lookout for that. But yeah, we'll take a look. Today we'll look at kind of maximum likelihood, use maximum likelihood as an approach for machine learning. And so for that, and we're gonna just kind of revisit least squares regression again. And the reason why we keep coming back to least squares regression is because it's like just a miniature version of so much else, right? Like if you think about what's happening in a neural network and what's happening with least squares regression, they feel like the neural network is like so much more advanced than least squares regression. But at the end of the day, it's kind of, you have a function that takes an input and creates an output, and then you have little parameters of your kind of your model, your function. So in least squares regression, you have, you've got your intercept and your different slope values. And for the neural network, you might have just like a lot more weights that you can adjust. But basically, it's just, okay, how do we adjust these things so that we arrive at these predictions where the predictions are close to the actual values? And so with that kind in mind, let's we'll revisit least squares regression, and this is kind of where we left off. And we just said, all right, our predicted values are just, we multiply our W times our X, right? We have the weights, basically your intercept, your slopes. You have your X values, and you kind of multiply those things and you add them together, and this gives you your predicted value. And then how do we figure out the weights to use? Well, we said this is basically t minus t hat quantity squared, summed up. That's our our mean squared error, or divided by n, mean squared error. And we're just trying to find the W's that are going to minimize this thing. And we can expand this out into matrix form, and we can say, okay, the W's that we're going to use for our model are going to be the W's that minimize, this quantity over here, right? So that's what, argmin over W is figure out the W's that are going to minimize this thing. Okay, and so so we do that, and basically we get, our least squares regression things, right? So and that this idea of minimizing loss we used to train the linear regression model, same way we trained the neural network. So even though the neural network, conceptually, I guess, or just as a model, is more complicated because it has more parameters, at the core, it's an optimization problem. It's a minimization thing. We're just trying to minimize the squares of the residuals. Okay, so we have we define a way for our model to make predictions based on some input X, some model parameters, and this here I have this vector W, but there might be multiple stages. We have some kind of loss function, and we've been using mean squared error, but it could be some other kind of loss function. But yeah, squared errors is frequently common, and then we estimate the model parameters by minimizing that loss function. And so with least squares regression, the model is simple enough that we could just do calculus and solve for the W's. But when it is more complicated and we can't do calculus and solve, we can use gradient descent. And gradient descent works for least squares regression. That's what you guys did in your second homework assignment. You guys did your gradient descent, and you came to the same answers as the linear model, right? And in the next homework, you'll do gradient descent for a neural network. but same kind of idea. But okay, so today we're going to do a different approach though, and rather than trying to minimize the loss, what we're going to do is try to maximize the likelihood. Okay, so it's another kind of optimization thing. Instead of minimizing something, we're trying to maximize something. And what are we trying to maximize? We're going to try to maximize the likelihood of our data. Now, I'm going to spend some time reviewing maximum likelihood estimation because just in my own statistics learning journey, it took me several times of seeing maximum likelihood estimation before I got it. And maybe some of you already get it, and it's like, oh, this is dumb and this is a waste of time. But in the past, when I would ask kind of questions about maximum likelihood estimation, it was clear that at least there's a handful of students who do struggle with this stuff, and so we'll spend some time kind of reviewing it because I want to make sure you have it down because you'll need it for this stuff. So even if you've seen it before, my apologies. We'll just kind of go over this again. Okay. So in maximum likelihood estimation, we have what we call a generative model, and we are saying the data that we observe comes from some kind of system that generates data, right? So we say, and that's what all of these kind of models are at the core. It's there's something complicated in real life, and what are the factors that go into determining how much you weigh at this moment in time, right? Like your weight. And there's genetic components, but there's also things like how much you eat and how much you exercise and this and that, and it's complicated, right? But we can simplify it and just say on average this is kind of what the average person weighs plus or minus some error value, and that would be a very simple way to kind of say this is how the values that we see, the values that we're recording, this is what it looks like, right? And for linear regression, well, if we use linear regression, we're going to say the actual values that we observe in our data are generated by taking weights, multiplying by our input values, and then we're adding some random noise. Okay, and again, this is a very simplified way because doing your weights times your input values really only take into account whatever variables you're looking at in your input, and probably the real life process that ties whatever available input values are to the actual values. There's probably a lot of things going on, right? Probably the true thing, maybe X needs to be 80 variables long or something to kind of account for a bunch of things, and even 80 variables probably won't account for everything. But you might have 2 variables or 3 variables in your modeling, and that's basically saying oh, these are the 2 or 3 most important X values that we take into account. And then if you take that into account, then you're only going to have a little bit of error left over to kind of brush away or explain away, right? So all of our generative models will always have some kind of random noise because rarely can we model everything. And if you do model everything, probably you've overfit your data. But anyway, this is what we have. So we say the actual values that we've recorded is the weights times our input values plus some random noise, and then and so this kind of the equation that we're using looks kind of similar to just linear regression, the linear regression model that we had when we were trying to minimize the loss function. The only difference is that we're adding on this epsilon, but really that is what makes all the difference. Okay, and effectively it comes down to the actual value is equal to our model's prediction plus the random error. Okay, and that's really the difference between the models that we're using. So in linear regression, we were just saying, okay, we just need a way to figure out our predictions, and we want to minimize the distance between the predictions and the actual values. Okay, but now in this kind of maximum likelihood approach, we're saying, okay, we have predictions and we have errors, and the goal is no longer to minimize the distance between this and that, but now we are trying to maximize, okay, if we take into account the different error values we see, how do we maximize the probability of these error values that we've seen? Okay, so we have the actual is the model prediction plus the random error, and now we want to talk about maximizing the likelihood of our errors, maximum likelihood and stuff. And that's because we're including this random noise, and we're going to say, well, the random noise is dictated by some kind of probabilistic function, okay? We have a probability function. And so the observations we have and kind of the random noise that we have, that's part of the data that we have, they come from some kind of probability distribution. And, in our probability distribution, we have different kind of parameters going to determine. And now we want to figure out, okay, how do we maximize the likelihood of our data, right? How do we maximize the likelihood of our data? And so, so that's what we need to do here. Okay. So here, before I forget, let me give you your first view quiz answer, which is the letter E. E as in elephant today. E. So when we do linear regression, what we're going to do is we are going to say this error term, the epsilon here, is modeled by a normal distribution. And we're going to say epsilon comes from a normal distribution where the mean is 0, and we have this variance term sigma squared. Okay, and so that's all we have. All right, so we're just that's going to be kind of our key and our key assumption here, and this is part of the reason why, when you took 101A and you did linear regression, when you check for model assumptions, you kind of want to make sure that your errors look like they're you have constant variance and stuff. I mean, the errors also have a mean of 0, but that's just going to happen when you estimate your parameters and stuff. Okay, but so if we combine this and we say, all right, we have some input values x sub n, and we have our model parameters w, and actually, sorry, there should be no subscript n there. Okay, so if we take our error terms, combine it with our kind of the mean function, which is our model parameters w times the input values xn, we can say, all right, the values we've observed come from a normal distribution where the mean is equal to w times xn with variance sigma squared. Okay, and so this is just my rudimentary, just crude graphic, and the idea is, what we're going to draw is, and this is even worse, but you draw kind of this blue line represents w times xn. Okay, and basically at each kind of location of xn, you have this little normal distribution. Okay, you have this normal distribution centered at w times xn, for each of these xn locations, right? And the values that we observe are basically draws from some random distribution like this. All right, and that's basically what we're saying right here. Okay, so now we have kind of this probabilistic expression for each observation in our data. And what we want to do is we want to pick our model parameters, okay? And so our model parameters are basically, you know, figuring out what the W's are, okay, to maximize the likelihood of seeing, you know, our data values T sub n, right? So we want to pick our model parameters to maximize the likelihood of observing the data we have. Okay, so this is where we're going to review maximum likelihood estimation. I think the key for maximum likelihood for me was recognizing that in maximum likelihood, we treat the data values as fixed, okay? We treat the data values as fixed, and the function, the likelihood function is a function of kind of your model parameters, right? Because when we think of probability functions, we often think of like, okay, what's the probability that the random variable x ends up being 7, or the random variable x ends up being some kind of some kind of thing, right? And you'd say like, okay, you know, if you have these two dice and you throw them, what's the probability you get the number 7? With maximum likelihood estimation, you're saying, okay, these are the values that we've observed, right? We rolled a 7, we rolled a 11, we rolled a 5, we rolled something like this. And based on kind of these numbers that we've rolled, you know, can you figure out which dice did I use? Did I use this dice that was like all 1s and 2s? Did I use the dice that was 1 through 6? Did I use the dice that was, I don't know, had different numbers on it and something like that? And so in that case, the data values that we've observed are fixed, and we're trying to figure out what went into kind of creating the data values that we've seen. Okay, so here in my example, I said, you know, let's pretend we've got some kind of pouch. Okay, I don't actually have marbles in this pouch, but we're gonna say I've got 10 marbles in this pouch. You don't get to look inside. All right, so you don't actually know the contents of the pouch. Okay, or actually. Oh, okay, no. In this first example, I tell you, we have 3 marbles that are red, and the rest are blue. So three red marbles and 7 are blue. All right, so in the first example, we have 10 marbles. We know what we have, and then we say, okay, we've got some kind of Bernoulli distribution, right? The Bernoulli distribution is theta to the x and 1 minus theta to the 1 minus x, meaning that if we're going to ask, okay, how many red marbles did we draw when I draw 1 marble? Okay, it's either going to be what's the probability of drawing red? That's going to be 0.3. What's the probability of not drawing red? That's going to be 0.7, right? So this is kind of how we could express that. And then if I say, what is the probability I get red, red, blue, all right, with replacement, right? So if I'm going to draw from this pouch a marble, a sequence of 3 marbles, and what's the probability to go red, red, blue? Well, if the probability of getting red is 0.3, then it's going to be 0.3 times 0.3 times 0.7, right? And so this is just the capital pi is to say the product of, and this is, you know, when you have a sequence of independent events, you just you take the product of all of their probabilities. So the total probability of the sequence of getting red, red, blue, or 1, 1, 0 for the outcomes is going to be, the product of, this function, theta to the x, 1 minus theta to the 1 minus x, and then when you do that, we get 0.3 times 0.7, okay? This is Bernoulli for this exact sequence of red, red, blue, which is different from binomial. In binomial, we say what's the probability of getting 2 reds out of 3 draws, which allows for different orderings, and so it'd end up being 3 times as much as this. But anyway, this is what we have. Okay, so that's a probability function. We say, okay, what's the probability of getting this particular data, right? So a probability function is a function of the outcome x. Right, we leave the parameters of the model. In this case, what proportion is red? We leave that proportion theta fixed, and we change the outcome. We say, okay, what's the probability of getting this outcome, red? What's the probability of getting this outcome, blue? What's the probability of getting the sequence of outcomes? And we multiply that. When you have a probability function, all of the different outputs have to sum to 1. All the different possible outcomes of x, probabilities of all those outcomes have to sum to 1. Or if it's a continuous one, the integral over all possible values of x have to integrate to 1. The likelihood function is different. Likelihood function, it's a function of the parameter theta. The data, x, we leave as fixed, and we change or we modify the parameter values that we have. We pretend we can modify what's happening inside, the bag, okay? And the key difference here is with your likelihood function for a given data set. For a given data set, the likelihood function doesn't need to sum to 1. It doesn't have to integrate to 1. And if your data just gets weirder and weirder, then yes, certainly it will not. The likelihood function is going to end up being a very small value. Okay, across all the different parameter values of theta. So sometimes if your data just ends up weird, no matter what you pick for your theta, the likelihood of your data is going to just be small. So we'll revisit our pouch with marbles, okay? And so this time in our pouch, we're going to say, okay, I don't know exactly how many marbles we have, or I don't know exactly how many are red or how many are blue, okay? But what I'm doing now is I'm going to pick a marble out and I look at it and I do it with replacement, and I get the following sequence: red, red, and blue. Okay, so we'll call red 1 and blue 0. All right, so again, this is the sequence of data I've seen: red, red, blue, and I can say, okay, what is the likelihood? Which it's the same thing as basically what's the probability of my data, except I don't have a fixed value for theta, right? So in the previous slides, we said it was 0.3 times 0.3 times 0.7. And yeah, if I plugged in theta equal to 0.3, this would be my likelihood. Okay, it would be 0.3 times 0.3 times 0.7. But we're going to leave it the possibility that, maybe theta is not 0.3, maybe it's 0.6, maybe it's 0.32, maybe it's 0.4, okay? And so if I told you what the contents of what the contents of the bag was, you could then figure out, what is the probability of getting that sequence, okay? The thing is we've observed this, right? So it's kind of, it feels a little bit silly to calculate the probability of something that already happened. So that's, we're going to call this a likelihood. And we're going to say, okay, what is the likelihood of getting this data that it got? And that's what we have here, okay? It's I think the part that's sometimes confusing is that the probability function and the likelihood function are the same. You're using the same kind of theta times 1 minus theta and all of these things. It's just from what perspective are we doing, right? So now the 2 and the 1 of getting the red, and the blue are fixed, and the theta is the value that can change, okay? So what we want to do is, we want to figure out what is the value of theta that's going to maximize this this likelihood, okay? So this is our likelihood function, and we want to know what value of theta maximizes this likelihood. So we could plot this across all of the different values of theta. Theta can be basically any value from 0 to 1, right? It's a proportion, so what proportion is in here, and then we could use calculus to solve. This is not so hard to do calculus with, but overall, as here, because it's just a sequence of 3 things. But if I had a sequence of say 50 draws or something like that, I have a big product, right? I would have a big product, and then kind of dealing with a big product can get messy. So one thing that we often do is we will take the logarithm of the likelihood function. So, and the reason again is, a likelihood function is frequently the product of a bunch of probabilities, right? Because when you have a sequence of independent events, the total probability of that outcome is a product. And so, so your likelihood function is often a very big product of a bunch of terms. And when you take the log of something, it turns the product into a sum. And it's a lot easier to deal with derivatives of sums than it is to deal with derivatives of logs. And again, because the log is a monotonic function, the values that maximize the log likelihood will be the same value that maximizes the likelihood, right? So, okay. So anyway, this is our next step is we take the log of the likelihood function. So we have the log likelihood, and that we statisticians, we just kind of throw that around, log likelihood, this and that. And again, the reason why is because taking the derivative of this is a little bit trickier than taking the derivative of a sum. But so what we do is we take the log of this and we say, okay, the log of theta squared times 1 minus theta is going to be 2 log theta, and then the times 1 minus theta will become plus log of 1 minus theta. All right, so the log of our likelihood function is this. And then we say, okay, well, what is the derivative of this thing with respect to theta? We're going to set that equal to 0 and solve for theta, right? So we say, okay, what's the derivative of this? The derivative of 2 log theta, so the derivative of log theta becomes 1 over theta, so 2 log theta becomes 2 over theta, and then we have the derivative of 1 minus theta, which becomes 1 over 1 minus theta, and then we have chain rule, so we have to multiply by a -1. And then, so solving for theta, I multiply this both sides by theta over theta, and 1 minus theta over 1 minus theta, with the assumption that theta is not 1 or 0, and we get theta equal to 2 times 1 minus theta. Solving for theta, we get theta equal to 2/3, right? And so this is the value of theta that maximizes the log likelihood, and it is the same value of theta that maximizes the likelihood itself. All right, is that okay? Kind of this process of maximum likelihood estimation. And so, again, whatever complicated model you have, right? And so you might have had to do maximum likelihood estimation for like a normal distribution and stuff. And, that one feels a little bit trickier because now you have kind of these two model parameters. You have a mean and a variance term, okay? And so that's, that's what we have to deal with here. So we said with our linear regression model, we say our data T comes from this distribution. The actual values come from a normal distribution where the mean is basically W times XN, and then we have some variance sigma squared. Okay, second view quiz answer is the letter B. B as in bear, B. Okay, all right, so we're going to say our observations come from this normal distribution, and we're also going to make another assumption, and we're going to assume that all of our observations are independent of each other, okay? And so, we often, in statistics, we just say, oh, okay, we're going to assume all of our observations are independent. And a lot of times that's a fine assumption to make. A lot of times maybe it's not. But that's going to be kind of one of the assumptions we're making. We're going to say, okay, all of these values that we observe, they're independent of each other. And then that means, the likelihood of the entire data that we have, we can just take the probability of each individual observation, and then we take the product of all of them, okay? And so, here, this is technically, this is a distribution specification, but just pretend this is the PDF of the normal distribution with these model parameters, right? So we're going to take the product of the PDF of the normal distribution with mean W transpose x of n for each input value x, and our arbitrarily chosen sigma squared variance. So we just have a product of all of these observations probabilities. Okay, so this is our normal distributions PDF. So we have 1 over root 2 pi sigma squared e to the negative x minus mu quantity squared divided by 2 over sigma squared. Okay, and this time our mu is going to be given by W transpose x. So that's our normal distribution here. Okay, so under the observations that all of these values that we see and the errors, okay, are normally distributed, we can say, okay, the product of all of the PDFs is going to be 1 over root 2 pi sigma squared. I can take the sigma squared out of the square root and just have 1 over sigma root 2 pi e to the, and then in the numerator, instead of x minus mu, I'm going to have t minus W transpose x of n quantity squared divided by 2 sigma squared. So I'm just taking that and turning it into a fraction here. All right, and so this is, I've got all of these PDFs and we have n of these terms, and we're going to take a big product of these things. Okay, that's going to be our likelihood function. And again, this is, if I say, okay, what we want to do now is we want to take the derivative of this thing, set it equal to 0, and solve for the W that's going to maximize this, we could do it, but it's going to be kind of messy, right? So again, dealing with the log likelihood instead is going to help us out, okay? So again, what we want to do is we want to be sure we treat this likelihood function. The only thing that we are able to mess around with is W. Okay, so this is, we're going to take all of our input values xn, all of the output values that we've observed t sub n, okay, those are all fixed, right? So maybe we have a data set where there's, or I don't know, we're looking at the that Olympics data set with the foot race, 100-meter dash winning times. So we have all of the input values x of n, which is like 1896, 1900, 1904, 1908. And then t sub n is like the winning race time was 12 seconds, 11 seconds, and 10 point whatever seconds. And so we're going to take, we're going to treat those values as fixed. We're going to leave sigma squared as just some kind of constant. Okay, so the observed value is t, the input value is x, those are all fixed. And then the only thing that we can really vary and change are what goes into W. What's our slope? What's our intercept? Okay, and we want to figure out what values of W, what is our slope and our intercept, that are going to maximize this function. Okay, so how are we going to do this? Well, we're going to take the, we're going to solve for it by taking the derivative, setting it equal to 0, and solving. Again, taking the derivative of this big product is messy, so we say, let's make our lives easier by taking the log. Now, again, it's like, is that really easier? Yes, it actually is. Okay, so everything gets messy, but it turns the big product into a big sum. Okay, and we say, okay, sums are easier to deal with. So we're going to take the log of this product, and we get the log likelihood, and now we have the sum of all of these terms. So the sum of the log of the terms, right? And so you look at each of these things, and you have 1 over sigma root 2 pi becomes, in the denominator, so you get -1, and then this is a square root, so it's -1/2 of log 2 pi. And then, and I took off the 1 over sigma, and I have minus log sigma, okay? And then this part, well, this part's actually kind of nice because it's e raised to this thing, so the log of this just becomes the stuff inside the e, okay? And then we have a big summation, and so we say, okay, what are the terms that vary over n, okay, that is different for each of these things? So this, we can just apply the summation just to this part, 1 over 2 sigma squared t sub n minus w transpose x sub n squared. So this is going to be different for each kind of observation we have. But the log of sigma, the log of 2 pi, these are just constants, right? And we have n of these things. So the total is going to be, we have negative big N over 2 of this, and then negative n of these things, and then these are all constants, right? So this is where we are, and we're going to say, okay, let's take the derivative of this thing with respect to w. We're going to solve for 0, and we're going to find the values of w that allow the derivative of this thing to equal 0. Okay, well, all of these things, when we say, okay, here's our log likelihood, what we're going to do is we're going to take the derivative with respect to w, and these are constants with respect to w, so they just zero out, which is nice. Okay, and then we have a little bit of kind of vector derivatives to deal with, and so the squared term cancels out with the 1 over 2 here, and then I have t minus this, and with chain rule, we're going to multiply by negative x sub n here. Okay, and we can kind of check our dimensions for each of these things, and so actually, in order for the dimensions to align properly, we're going to have the x sub n out here, and we get x sub n is 2 by 1, and then t sub n is for each observation n, we have 1 over. It's just not a constant, just a single value, right? And then w transpose xn is also a single value, because we want the derivative with respect to w to be 2 by 1. Okay, so I'm going to transpose this term. Okay, w transpose xn, it's a single value, so I can transpose it and I get xn transpose w. And then I'm going to distribute the x sub n here. Okay, so I've got x sub n times t sub n minus x sub n times x sub n t times w. And so I have, I write the dimensions underneath all of these things so we can kind of make sure we're not cheating around with just throwing terms around all over the place. So it's good to have the dimensions line up. So that was one thing, like on the midterm exam, you had this lambda term that you had to kind of combine with this 2 by 2 matrix, right? You can't just say, all right, we're going to just add the lambda times the 2 by 2 to the 2 by 2 matrix. You had to multiply it by a 2 by 2 identity matrix to kind of do that. So some of you lost some points there, but just only a few. Okay. All right, but anyway, we've got to make sure our dimensions line up. So this is so far so good. And then we say, okay, well, can we get rid of this summation term? And so this looks scarier than it is. All right, so this is what we have, and we're trying to. So this is the previous slide. Okay. And so I'm just taking this. You're going to see this at the top, right? This is what we had on the previous thing. And then I'm going to kind of break out the summation, break the summation apart, or this, I guess, this sum of differences to a difference of the sums here. And then I'm going to just say, okay, can we, if we look at what is x of n, right? X of n is basically, if we just treat it as a slope and intercept, and it will generalize to multiple terms. Okay, so each x of n is a 2 by 1, and if I expand x of n to big X, okay, now I get this n by 2, right? This is the big X matrix is n by 2. Okay, each t sub n is a single value, and when I expand t to I get a column matrix, an n by 1 matrix of t, and then the w itself is a 2 by 1 matrix of the kind of slope and intercept, or intercept and slope here. So let's take a look at this term, the summation of x of n t sub n. Okay, this is a 2 by 1 thing, and we can, if I expand to big X, all right, that's going to big X transpose, that's going to be 2 by n. I can multiply that by t, which is n by 1, and we're going to get a 2 by 1, okay? And we can ask, is this equivalent to the same thing as doing x of n times each t and then summing them up? And we can say, oh yeah, I'm going to take t times 1 over x, x1, and then t2 times 1 over x2, or times 1 times x, t2 times 1 and t2 times x2, and then t3 times 1 and t3 times x3. Is that the same thing as doing this times this? And it is, right? So if you take x transpose and you multiply it by t, it's going to be, t1 times 1 times x1, and t2 times 1 and x2. So all of those terms align, and this computation makes sense, okay? We can do the same thing with our xn transpose w, and we say, okay, for our first thing, we're going to do 1 times x1 times 1 times x1 times, w0 and w1. So we're going to get like 1 squared plus what do we get here? Something, right? Times, I guess 1 squared times x1 squared times w1, and 1 times w0, and so we do that, and we say, okay, can I just expand these to our x's, and also yes, right? So we can expand each of these x's to x, big X and big X. So we have big X transpose big X, which is going to be a 2 by n times an n by 2 times our w. And again, if you kind of look at each element and you think of, all right, what is it for n equal to 1? What is it for n equal to 2? The summation of all of this is equivalent to doing these matrix operations here. Okay, so I can now combine this and this, and we can say this whole thing simplifies to this in matrix terms. So we just got rid of the summation sign, so we don't have to deal with the subscript n. We have these summation terms. Okay, all right, and does this look familiar? All right, so we can say we're gonna set this equal to 0 and solve for w, right? And then at this point, well, if we set this equal to 0, it really doesn't matter what sigma squared is, okay? It really doesn't matter what sigma squared is. And when we solve for this, we get w is equal to x transpose x inverse x transpose t, right? If we solve for this, right? Because this part, I mean, we didn't have the 1 over sigma squared before, but this part is exactly the same that we got like when we were trying to minimize the mean squared error. So this solution, it's the exact same values for w hat, right? That minimized the mean squared error when we did this back in week 1. And yeah, that kind of points to this thing that minimizing the sum of squared errors, or minimizing your mean squared error, is equivalent to maximizing the likelihood, right? The key assumption here is the likelihood is under the assumption that the errors come from a normal or Gaussian distribution. Okay, the variance sigma squared doesn't appear in the solution at all right, and doesn't, whatever variance we have doesn't actually affect the model parameters. Okay, the only thing that we needed was those variance terms to be constant, so that they go. All right, and actually, if you look at the likelihood function, okay, right. So this was our likelihood function, and then when we took the log likelihood, what happened, right? This part, we got these constant, these terms that are constant with respect to w, okay? This is also a constant. This is a negative value, okay? And then what is this? This over here, this is the formula for the sum of squared errors, right? This part over here is the formula for the sum of squared errors. And so when we say, hey, we want to maximize the log likelihood, okay, basically it's saying the same thing as I want to minimize this thing because it's being multiplied by a negative constant here, right? So when you look at the formula for what is the log likelihood, or the likelihood, maximizing the likelihood function, okay, or in this case the log likelihood, is exactly the same as minimizing this quantity, which is the sum of squared errors, right? And so again, this only works out because we have this term up here, which is part of the normal distribution. Okay, but that's what we have. Okay, so we'll wrap it up here. But here we kind of just went through this process of trying to maximize the log likelihood function, or likelihood of this model, where we're saying the values come from a normal distribution centered at W transpose xn with Gaussian error terms, and maximizing the likelihood is the same as minimizing the sum squared errors here.
So when we ended up with this SSE, did we transform that SSE into like the matrix notation where it's like T minus W?
Like
perform our
we could have this was we could have done that too. We could have just recognized like, oh, look at this, and we could have just done T minus XW transpose T minus XW. Yeah, exactly. We could have done that too. So I guess another way, another approach, right? So, but yeah, you could look at all of those things. Okay, last view quiz answer is A as an apple. A as an apple. And we'll wrap it up for here, okay? Be on the lookout for homework 3, and we'll see you on Wednesday.